Yeah, again, sorry for the interruptions. Mother Nature really threw us a curveball here. I'm looking out my window. There's dozens of trees down and limbs, and we had hail and lost power, and I don't know if a microburst or something like that. But anyways, let's see. So yeah, tonight is the second session of your MGIS Capstone presentations, and each of you will have, I believe, I'm kind of going off of what I did last time. You'll have 15 minutes total for the presentations. Is that the correct time period here? I think.
I think I saw an
Correct.
email saying 13 minutes, and I was going to wonder
Well,
how strict is that?
12,
Well,
I was on the session this afternoon. It was 12 minutes for the presentation, about 3 minutes for questions.
okay. Yeah, I'd like to try to keep that as firm as possible, and the reason being is that uh, we all have compressed times and people have schedules, and I think we should honor that time allocation. So it would be ideal if you could do, yeah, 12, 13 minutes with a time for a question or two, and then we'll keep moving right on. Um, so let's do that. Uh, I believe, let's see, Sarah, I think you are up first.
Yep, looks like
So
it. I'll try to keep this nice and brief.
yeah,
Keep
that would
this
be
going.
very, very helpful. So if you want to go ahead and share your presentation, we can make sure it's
Yeah. Let me
working.
get this here going. Oops. Oh, maybe that fix it.
Let's see.
Oh, you know what? Let me try something. Sorry, 1 second. There we go. All right, you guys can all see this okay, right?
It's working its way. We don't see anything yet.
Loading in, hopefully. Still can't see it?
Yeah, not yet.
Let me hit screen share. How's that?
Yes,
Okay.
yes.
All right, let
Perfect.
me just
Perfect.
minimize this up here. Okay. So yeah, I'll just keep this brief. But again, my name is Sarah Rothenberger. My project, excuse me here, it is titled Spatial Justice in the Garden State, a GIS-driven analysis of Superfund site clustering, risk, and disparities. So just quick background, for those that may not be familiar with Superfund sites, the Comprehensive Environmental Response Compensation and Liability Act, which is more commonly known as Superfund, was enacted by Congress in 1980. Basically, it's really to address hazardous waste sites by holding polluters accountable. And if they can't be held accountable, it gives the EPA the authority to allocate funds or resources to remediate those sites. For my project, I decided to focus on the state of New Jersey solely just because it has the most active number of sites across the country. As of December 2023, that was 115 active locations. Goals for my project including a hotspot analysis to analyze the spatial clustering of Superfund sites, assessing environmental risk, which was focused on examining proximity to waterways, and then evaluating demographic disparities. This focused on social vulnerabilities and whether or not people with various numbers of social vulnerabilities are more likely to reside or just be situated near these Superfund sites. So some previous research real quick, a really big key theme that popped up kind of across the board was showing that race and income are major factors influencing where Superfund sites tend to be placed. One study in particular, which I saw several times, was the study from Marinville et al. In 2009. They did a study in Illinois and they determined that race rather than income was actually the primary determinant in site distribution. A couple other studies had followed up on that. Burwell Nanny et al. Also identified, but in South Carolina this time, that 15 to 20% higher non-white populations existed in census tracts with Superfund sites. As far as the spatial distribution of Superfund sites, that Marinville study, again, like I said, it kind of reoccurred, came up pretty frequently. They also found a disparity radius, which was about 1.5 kilometers around the Superfund sites where minority populations were overrepresented. And then a lot also discussed how historical contamination was a big factor. New Jersey plays a big role in that, the Ironbound district, kind of up in that Northeast region, Newark area. They have a very rich history of chemical manufacturing, steel production, stuff like that, which is kind of still lingering around and has led to the contamination levels we're seeing today. And then a couple other studies, Mean, Nelson, and Dougal, as well as Berry and Haltmeyer's studies, discuss the importance of talking about public health outcomes and public health risks as well when it comes to distribution of Superfund sites. It's not something I focused on in my project, but it is very important to discuss when dealing with Superfund sites. And then real quick, just for environmental risk, two big studies. I may mispronounce this, I apologize. I believe it's Kiagdi et al. Their 2021 study did discover the importance when looking at contamination spread that flooding plays a role, especially when it comes to the health risks and that public health outcome in the nearby communities. And then one interesting thing, the Katsuma and Katzenberg study in 97, they discussed the importance of looking at future land use assumptions when taking into consideration environmental risk, primarily because if future land use in these areas were going to be residential zoning versus industrial, that made a huge difference on risk assessment. And they argued that's why future land use assumptions should be in environmental risk assessments surrounding Superfund sites. And then just socioeconomic disparities, a couple different things. Viscusi's study really analyzed cleanup expenditures. They talked about how, similar to Hurd's 93 study, wealthier areas just benefited more from remediation efforts and just kind of left low-income communities at higher risk and just kind of let them bear the burden of cleanup costs. And then one important thing for my project, a means study in 2018, they put an emphasis on the fact that most studies are done on individual sites, Superfund sites, and not many do a large statewide or larger region pattern analysis, which is why I decided to focus on New Jersey as a whole and not just one or two particular sites. For my data, I had three main data sources: the EPA's National Priority List for my actual Superfund site data. This data includes information about the site contamination types, if they're in remediation, if they've been deleted off the list, when they were nominated, all of that. The New Jersey Department of Environmental Protection. I sourced all of my hydrology data from that, so that was all the waterways, streams, rivers, bays, etc. And then the Census Bureau, I sourced not only my state boundary and census tracts layers for the cartographic boundaries, but that is where I got my demographic data, the community resilience estimates. So this is kind of important. I initially was going to do individual variables and make my own overlay analysis, but a peer of ours, Gabe Branch, actually made a recommendation that I consider using the community resilience estimate data, which I ended up doing. Basically, what this data does is it includes these 10 variables here. So it's a range of income to poverty ratio, limited vehicle access, broadband internet, all kinds of things. And it classifies the census tracts based on the rate of the population that they're experiencing any number of these variables. They do classify into three categories. So those are the rate of people experiencing 0 vulnerabilities, 1 to 2 vulnerabilities, and then 3 or more vulnerabilities. And I use this just for simplification purposes, just so they could kind of get a more in-depth, broader view at the socioeconomics of each census tract in each area without having to make individual layers for each individual demographic variable otherwise. This isn't really analytical per se. This is kind of just an overview, a symbology-based heat map of the Superfund sites layout in New Jersey. You can see, a more dense area up here in that Newark, Northeast Jersey area where that Ironbound district was. Just wanted to point that out. As far as my methodology, other than the standard gather and clean data, there were three main parts. It was that hotspot analysis, the proximity analysis, and then that demographic overlay analysis. Results from my hotspot analysis. So I just used the Geddes Ord hotspot analysis for this. What I was able to discover that those clusters, they did show up in those historically industrial urban centers, which date back to, early 20th century, mid 20th century. This area up here in the Northeast didn't have as many hotspots as I kind of expected it to be, just looking at like the heat map. They were more down here in the Camden area. They did have a confidence level of 90 to 99%, somewhere between, up here and down here. There were a few smaller clusters, in central Jersey, and then also up here in the Northeast. And then this histogram here really is just an idea, kind of layout of the site scores, which is how I did the clustering, was based on the site score. Higher site scores indicate higher risk. So scores ranged throughout the state anywhere as low as 28.5 up to 75.6. The median was about 45, mean is about 44, 45-ish. So kind of right there in the middle. For my proximity to hydrological features, so what I did for this here, I put 1 mile buffers around Superfund sites. 1 mile was kind of just chosen as just because there's no real reasoning behind that, to be honest. But what I did discover was that in key areas, specifically down here along the Delaware River in Camden and Philadelphia, just in this one partial section, there's a few towards Trenton more, but this one section alone, there were 8 Superfund sites just in that one area. And it's important to note because the Delaware River does provide drinking water to municipalities in the Delaware River Basin and the Delaware and Raritan Canal, kind of similar up here to the Newark Bay area, the Hudson River, Raritan Bay, and then the Newark Bay, where contaminants do transport into like marine environments, commercial fisheries especially. So altogether, looking at this, there were about 2,600 segments of water features throughout the state. It's about 6.4% roughly where Superfund sites did intersect within a mile of waterways, which really is important, especially when it comes to that contamination spread and downstream how it travels. This here is just the result of the Moran's index for each variable for the social disparities. This top variable here is for those experiencing no vulnerabilities. So these areas, they're high rates of low vulnerability. They do tend to cluster together around Superfund sites, or in this case, lack of Superfund sites in those areas. It is statistically significant. It's not due to random chance. The others were also very similar. This second one here, the PRED12PE, that is the rate of individuals with 1 to 2 social vulnerability variables. For this one, it's kind of the same thing. There's a positive spatial autocorrelation, similar values of vulnerability. They are clustered rather than randomly distributed around those Superfund sites. And then for those experiencing 3 or more social vulnerability variables, this one is statistically significant as well. They do have a positive correlation of higher chance of being clustered around those more densely populated areas or more densely covered with Superfund sites. And then this here was just a little bivariate map I did for the Superfund and social vulnerability. I wanted to focus really on comparing the 2 extremes. So I focused on the rate of individuals that are experiencing no variables of vulnerability and then those experiencing 3 or more. You can see up here in that Northeast region again, where Newark is, the Ironbound district. It's very high. The darker reds and purples, representing that higher vulnerability. And then the blues indicating lower vulnerability. Up here, it's a little more sparse with the Superfund sites. So there's definitely, something going on where the closer they are to Superfund sites, it's kind of tracking across the board. It was what I kind of expected to see. That again, minority populations are typically surrounded by Superfund sites and then are also experiencing more social vulnerabilities. And then just some quick conclusions. That community resilience estimate data was definitely better than individual variables for an overlay analysis. We did find out that the overlap between Superfund sites, vulnerable communities, and major water infrastructures was there. The urban centers, again, Newark and Camden, they definitely show clustering of higher vulnerability populations. And then as far as limitations go, that 1 mile buffer was overly simplified, I think. It doesn't fully account for like range of contamination pathways like groundwater, migration, and airborne dispersion. But I just kind of did it to be simple. And then the CRE data, it was very static. That was one thing I was concerned about. It doesn't really reflect recent shifts in the community. And then the aggregation of the data with that community resilience estimates also kind of obscures intra-tract disparities or even the lived experiences of risk. And then again, future work, like I mentioned before, linking contamination to health outcomes and integrating things like climate risk and then also amplifying community voices of people living in those areas would be great areas to kind of focus on in the future. And that is all I have. Thank you.
All right, thanks, Sarah. Good job. If anyone has any questions for Sarah, if you can either just speak up or type them into the chat window, we can entertain those there. And then Sarah, if they do appear in the chat window, if you could read them before
Yep.
you answer them, because the Zoom doesn't record the chat window, so that
Yeah.
would be helpful. So I guess one question I had is, and maybe I wasn't quite following along. I guess I wasn't sure how the hydrology component, um, the social vulnerabilities component sort of worked into the Superfund assessment, especially with this idea of risk.
Yeah, so for the proximity to waterways, I was kind of just looking at how close they were to waterways. I wanted to incorporate some type of not necessarily risk assessment, but some way to show that that environmental justice aspect, that Superfund sites do cause risk not only to communities' public health, but also environmental health as well. So that was kind of more just another part of my project was just viewing how close they were to waterways and what those implications were from that. And then the social vulnerability aspect of it, I didn't do anything with the social vulnerability and the waterways, the proximity to waterways, they were kind of separate. Um, was there something specifically about the social vulnerability that you were asking about?
Well, uh, I guess from my one overarching question is this definition of risk.
Mhm.
You see a lot of papers and research talking about risk, and it's never really overtly defined what risk is. So is it like a risk to people's health or livelihood or you know whatever factor is being studied. So I guess I didn't know if there was some sort of overarching risk definition that you were operating under, or whether you were treating risk as more kind of like a generic um, idea.
Yeah, it was definitely more generic in my case. I just kind of wanted to lay out, like I said, that risk to environmental exposure with the waterways and then risk to individuals living in and around Superfund sites. I just kind of wanted to see whether or not people who, in New Jersey's case, if people living around these Superfund sites did follow the trends in other places where they were just as vulnerable and had just as many social vulnerabilities, all those variables that is included in that community resource estimate data. I just want to see if kind of the patterns tracked, not necessarily any particular type of risk, which I know, like I said, the public health outcome risk is something that a lot of the previous research talks about and focuses on. It's not something I focused on in this case. I was kind of limited with scope at the time and a time frame. So I just
Sure.
kind of wanted an overarching just to see, what it was like in both things, the people living there, and then also, like I said, the proximity to waterways.
All right. Well, thank you for that explanation. If you could put your your email in the chat window if someone has a follow-up question.
Yeah,
And
absolutely.
then I think Zach, you're next up on the schedule. So if you could start sharing your screen, we'll move along. All right, we can see your screen. So whenever you're ready. We can't hear you.
Yes, because I was muted. All right. Okay, so my name is, and y'all can hear me now?
Yeah, no problem.
Okay, cool. Thank you very much. All right, so my name is Zach Long. This is my Geo 87 capstone project.
I am no longer able to hear Zach.
Yeah, and Zach is gone. I don't know where. Oh, there he is. He must have left. Are you back, Zach?
I can hear you. Can you hear me?
Well, yeah, but your screen disappeared.
Okay. Okay, so let me exit out
So
of
your
this.
internet is unstable, or because you were
No?
going fine and then it just went away.
Okay, let me try. All right, let's try this again. Beginning. All right. Can you see my screen?
Not yet.
Okay. Sure. Okay, from
Okay.
beginning.
Well, I see your screensaver.
Okay, see the. Okay,
All right, there we go. There we go.
okay. So I'm just going to do that there probably. Okay, so this is my capstone project. Review farm park shoreline erosion analysis, monitoring shorelines in an urban landscape. So who I am, my name is Zach Long. I am a GIS specialist and SUAS pilot for the city of Newport News in Newport News, Virginia. My work duties are split fairly evenly between drone work and GIS work. When it comes to drones, I fly non-law enforcement drone missions for the city, supporting various departments such as Public Works, City Manager's Office, Planning and Development. For GIS duties, I do a lot of data maintenance, especially for the stormwater and wastewater side of things and the tax parcel layer and various map creation. So nothing fancy or sexy, but it's work that's got to get done. So it is what it is. So for this project, I wanted to look at shoreline erosion because it is a common problem for many municipalities, Newport News being an example because we are along the Chesapeake Bay. And addressing it, as you can see, is filled with various different challenges. It's expensive, it's resource intensive, often requires specialized expertise to remediate correctly. So being able to monitor shoreline erosion and shoreline movement is important, but doing so has its own issues and difficulties. So the basic idea of this project was to create a script that would live in ArcPro that would allow a non-GIS power end user to be able to open the project, go to the script, enter in the years that they want to take a look at using city aerial imagery, and then that script would essentially be able to select the subject area that they're interested in, do a shoreline analysis, and spit out those results and let them start looking at that change over time. And the study area is Riverview Farm Park, which is a city-owned park in the central part of the city. And this area has seen a fair amount of shoreline erosion over the years. With the literature review, it's kind of mainly looking like why is it important to monitor shoreline erosion? Obviously, shoreline erosion presents a large number of different risks, and a well-maintained shoreline provides a wide-ranging number of different benefits, as I've listed. And shoreline erosion is often caused by so many different sources. And a factor in today's world is that these factors that cause shoreline erosion often act together, especially in hurricane events, which is common here in Virginia on the East Coast, and they are being supercharged by climate change. So they're doing more damage. So when you're looking at the different type of data types that are used for shoreline erosion monitoring, you're mainly looking at survey data, LiDAR data, visible and non-visible light photography. And these are the three main ones really used because if you're trying to use GIS to do this, these are the ones that are best integrated into GIS. There are other historical resources you can use like charts, land-based photography, but they are harder to integrate into GIS for any type of real good analysis. So for this particular project, my goal was to use city-owned plane-derived imagery. So this is all imagery owned by the city. And the idea is that this imagery has already been cleared for cloud cover and corrupt data. So there's pretty much no pre-processing that needs to be done to it. And it's using leaf-off imagery, so you're not getting that clutter from the leaves. And as you can see, the city has a decent amount of historical data. To move that a little bit. Oh, decent amount of historical data that covers a good amount of time, even mainly the 2000s, but still that's enough to start doing some analysis. One thing I did learn midway through this project, that this data only has red, blue, and green bands. There's no near infrared bands or anything else. That is just a limitation of that was a limitation of the data, which will come important a little bit later in the presentation. There we go. So what you're seeing here is pretty much my study area. This is part of the shoreline of Riverview Farm Park. This is a clipped raster from 2001. So this is the first color photos that the city has available in its catalog, basically. As you can see, poorly defined beach area, a very large marsh area with a stream going through it. More poorly defined beach area. This is pavement that belongs to a wastewater treatment plant that is on the site, and another stream that goes along here, and it's out of the area, obviously, but it goes all the way further back into it. If you Google Riverview Farm Park on Google Maps, you should be able to kind of see this creek. I believe it's called Governor's Creek, if I remember correctly. So here is a clipped raster from 2013. So as you can see, there's been some shoreline fortification along here with the rocks, more shoreline fortification here. There has been a massive amount of shoreline erosion here. This was all marsh area. Now it's water, and there's been a beach replenishment effort by the city. But you still have some marsh back here, and what happened is that you had water rushing over here and degrading the shoreline, and same thing here with Governor Stream over this way. This is 2004. This is what the shoreline's actually going to be looking like, because it's gone under a massive amount of shore fortification and rehabilitation. You've got ripraps here. There's a living shoreline along the beach area here. It's been U-shaped to help better absorb wave action. You have a large amount of rock and riprap along this shoreline to stabilize it. You have further riprap and rocks along here. Governor's Stream has been rerouted, so it's going to be flowing out here and a look to be a bit slower. And the stream itself is going under a further restoration project that is outside of the scope, so that will help slow this and make this less destructive. And the marshy area here has been essentially diverted, so stormwater pipes are essentially channeling the water underneath the shoreline instead of over the shoreline. So the idea, the first way I tried to look at this was to create my area of interest, use this, then use the script to clip the rasters by that area of interest, perform an unsupervised classification, then convert those from raster to polygon, raster to polyline to start to do my analysis. And the power of the script idea was that this would iterate through the entire folder where all this data is located. So like I said, the user would go in, select the years that they want, and the script just goes through all of it and just automatically does this unsupervised classification. And the other thing it would do is that not all of our city imagery has a spatial reference. So the script would also check the imagery for a spatial reference. If it didn't have the correct spatial reference, that the area of interest has, it would create a copy of the raster, assign that spatial reference, and then proceed with the first step and delete anything that is not being used in the analysis. So you're not ending up with a ton of unnecessary data. So this was the result from my 2024 unsupervised classification. As you can see, the interior around here, which was land, is being classified as water. Red is supposed to be land, gray is supposed to be water. This area around Governor's Creek isn't too bad. This area is not too bad, though. There's some boardwalks and other things around here that should be showing up as land, but it's showing as water. And as I went into different years, the errors continue to increase. And despite changing classes, intervals, sample size, I was never able to get a really good clean data set with unsupervised classification, which led me to my second attempt, which was same step as the first, but second step was using raster math to create a near infrared light band using the blue and green bands, and from this creating a water mask and converting that water mask from raster to polygon once again to try to start doing that analysis. This is from 2024. You've got the water mask here that's been converted to polygon. That's the actual water mask. Once again, not the best, unfortunately. This is a big limitation of the data of only having red, blue, and green, and not having that near infrared or infrared band that I could just do I could do a vegetation analysis with it. I mean, the mask itself is not bad, but the conversion to polygon is not good, and that's something that would not be useful for an end user to do any type of analysis off of. 2013, even worse results, essentially. Once again, just limitation of the data that I had. So at that point, even trying to adjust things up and down, it was pretty much rearranging chairs on the Titanic, so to speak, and just couldn't get a good, clean data source that I would feel confident handing over to someone for analysis. For the conclusion, so to quote Mythbusters, if anyone's watched that show, failure is always an option, which for half of this project, failure was. I was not able to create a workflow that would be able to create that good, clean data set that I could give to an end user to do analysis. I was able to create 2 scripts, which I am fairly proud of myself because I'm not the best at scripting and doing that type of stuff. Kind of going into the future research or future work on this, I'd probably just modify this so I can use Landsat or another data source that has that near infrared bands and see what I get with that, or maybe do a classified training, though if I'm trying to make this user-friendly for a non-power GIS user, just modifying it to use Landsat and use that near infrared band is probably going to be the best way to go. Some of my sources, and that is me. Any questions?
All right, Zach, thanks a lot. Great presentation. Looks like you have a question in the chat window.
Okay, hold a sec. Let me get the chat back up. Chats. Okay. So in your supervised on classification, how is the riprap shoreline identified class type? So I was just trying to do it as lands. I grabbed a Esri workflow that was using a much cleaner and more pristine beach area along, what was it, Assateague National Park up in Maryland's as kind of my basis for my first one. So I was just trying to work with 2 classifications, land and water. So the riprap would have gone into that. And it did a decent job with the riprap. It's just it was having a lot of issues with I think the big issue was just the vegetation, especially like the grass and what leaves there were. It was just because it was so reflective, it was classifying that as water instead of lands.
I have a question.
Yeah.
So you used unsupervised image classification, but was it object? I didn't realize, I didn't see. Was it object based or pixel based?
Pixel
Okay. And so you had two different classes, one water and
and one
one was
land.
just general
Just
land
land.
use.
Correct. Just land, yeah.
Okay. Because I'm wondering if it's possible to, like, if erosion can happen on different types of land use types at different rates. Because the ultimate goal, I think you said, was to provide a data set that other people can use for a rate of change study, right? Like a shoreline rate of change study.
Yeah, the idea is that this wouldn't be exhaustive, but basically give the end user a good idea. Like, hey, there's been some erosion here that looks a little bit more severe than we might expect with like just normal shoreline erosion, because that's always going to happen. And then that would be like the emphasis, like, hey, let's get a contractor out, get a specialized contractor out, or let's get the survey crews out. So just being able to do a little bit of, I'm gonna say, a little of analysis before sending people out, because doing this type, especially with survey crews, doing a survey to monitor to get detailed information about shoreline analysis is very expensive. So anything you can do in the office beforehand is, even if it's not the most detailed or advanced, is still very useful.
All right, Zach, thanks again for your presentation. If you could put your contact info in the chat, that'd be helpful.
Mhm.
And then I think Priscilla, you are up next.
Yeah, can everybody hear me?
Yes.
Okay, great. I'm going to share my screen. All right. Can you all see PowerPoint?
It's working. There we go. Yep, yep.
Okay, great. Let me just try and there we go. All right. Can you all see the title slide?
Yes, you're good to
Okay.
go.
All right. So my name is Priscilla Montalto, and this is my capstone presentation titled Identification of Graves Using Multispectral Imagery and Geobia Analysis. So just to start off with a personal introduction, I began my career working as a satellite imagery analyst at Digital Globe and Maxar. I was the GIS specialist for my county's emergency response center and the manager of a flight planning team for an aerial imagery company. And then my current role is as a project manager for NV5 Geospatial. And most of my projects involve LiDAR and imagery acquisition for utility clients. All right, so as far as an introduction for my project, I became interested in this topic of remote sensing in the field of forensic investigation because I wanted to link two separate interests, one being the rise of publicly available imagery, and the other being volunteer-based organizations like NecroSearch, which focus on finding missing persons and clandestine graves. This led me to my question of whether publicly available imagery could be used to identify graves. So this question was then transformed into my more specific project goals and objectives. The goals of my project are to identify cemeteries within publicly available multispectral imagery, identify clandestine graves within publicly available multispectral imagery, assess the accuracy of the identification by comparing the classification results to ground truth, and then to compare how accurate this approach was in identifying cemeteries versus how accurate it was in identifying clandestine graves. And then to do the same thing and compare how accurate the approach was when applied to different multispectral sources. So, kind of getting into a more formal literature review, I began by looking at existing articles on the general field of forensic investigation. I found there are downsides associated with traditional approaches like line searches and cadaver sniffing dogs, especially considering the time and resources it takes to deploy people into the field, as well as the potential damage these methods can cause to crime scenes. These issues with traditional methods of forensic investigation have resulted in a rise in interest in less invasive approaches, which brings us to existing studies that use remote sensing to locate graves. So many of these studies focus on terrestrial approaches like electromagnetic profiling and ground penetrating radar, but these terrestrial approaches still require field visits, so it became necessary to look into airborne approaches. So airborne approaches include methods of capture using helicopters, fixed-wing aircraft, drones, and satellites. And in the literature, there's some debate as to the relative effectiveness of each type of airborne approach, and each have various trade-offs relating to spatial resolution and image footprint size. Then there's also discussion in the literature of what spectral resolution of imagery is most useful. So most of the literature really focused on how good hyperspectral imagery is for grave detection, which makes sense if you consider that the types of soil changes indicative of things like decomposition are associated with very specific spectral signatures. While multispectral data might not be detailed enough to differentiate between exposed soil and other land cover types. So while hyperspectral imagery is really useful in these applications, the downside is that the data can be time consuming to analyze. So there was this opportunity to reconsider multispectral imagery as an alternative. So for this project, I also looked into existing research regarding computer-aided methods of analyzing imagery to detect graves. And these methods can be categorized as pixel-based or object-based. And the images on this slide do a good job of showing visually the difference between these methods. So pixel-based methods of image analysis give a classification to each individual pixel without any consideration for the attributes of neighboring pixels, while object-based image analysis first groups pixels into objects based on similar spatial and spectral characteristics. So going back to the literature, the majority of relevant studies focus on using this pixel-based method to do things like identify cemeteries within imagery, while there really haven't been any studies utilizing object-based methods. So, now that I've gone through that existing literature review, I wanted to reiterate where there's a gap in the research. So we kind of started with this discussion of how there are these traditional methods of forensic investigation which have their flaws. So that directed us towards less invasive remote sensing methods. But a lot of those methods are terrestrial and involve physical site visits. So I started looking into airborne methods of capture, and especially satellite imagery, because it's more accessible, but historically it's been discounted for not having a high enough resolution. Then I considered whether this aerial and satellite imagery should be hyperspectral and multispectral, with multispectral being easier to analyze. That justified further investigation. And then finally, we've got this method of image analysis to consider. And with most of the literature using pixel-based methods, that leaves the question of how object-based methods can be used for analysis. So basically, what I end up with is a rewording of the title of this capstone. So OBIA analysis of multispectral imagery to detect graves. So now that I had this project objective, what data was I going to analyze for this project? So what I did was I chose two separate areas of interest, the Mount Hope AOI and the Douglas AOI. I'll explain more why I chose these sites and the differences between them in the next few slides. But I did want to just orient everyone with this table of project data. So what I have listed is the 12 data sets that I used. So that's 6 data sets for Mount Hope and 6 data sets for Douglas. So with this Mount Hope AOI, why did I choose Mount Hope? Mount Hope is a cemetery that's located in Rochester, New York. And I chose this site because I live close by and I was able to go out to the field to collect coordinates of actual grave locations. So moving on to the Mount Hope imagery data sets, I have NAPE imagery and high resolution aerial imagery here. And then I also used a satellite imagery data set. So the second AOI, which I call the Douglas AOI, is the footprint of the NecroSearch facility in Douglas County, Colorado. Why did I choose this second site? I mentioned NecroSearch in the beginning of this presentation as being an organization that focuses on the search for clandestine graves. And what their Douglas County facility does is that they have this sort of study area where they bury pig carcasses to simulate human burials, and then perform various tests on the area to improve detection methods. So when I started designing this project, the difficulty that I ran into was how to find an area of interest that I knew to contain clandestine graves. And this NecroSearch facility was my solution. Because I was able to reach out to them and they provided me with the actual coordinates of each pig burial. So in contrast to the Mount Hope AOI, which is a cemetery, but is not representative of clandestine burials, this Douglas AOI is. So just like the Mount Hope AOI, for the Douglas AOI imagery data sets, I have NAPE imagery and high resolution aerial imagery, as well as a satellite imagery data set. All right, so I covered the data that I analyzed. Now I'm going to get into methods of analysis. I use software by Trimble called eCognition in order to perform this object-based analysis. The workflow begins with pulling imagery into the application, using algorithms to perform segmentation, which groups the pixels of the image into objects. And you can see examples of segmentation outlined in blue on this slide. So I wanted to take time to quickly mention that it was at this segmentation portion of the workflow that I discovered that my satellite imagery data sets would not be usable past this point, since pictured here on this slide is the segmentation result that I was getting. And this is segmentation of the entire Mount Hope area of interest. And we can see that the spatial resolution is just way too coarse for meaningful grouping of pixels to be created. So after the segmentation part of the workflow, we have object interpretation key creation. This slide shows 2 of my object interpretation keys that I created, which is where you choose representative objects from each class that you want to create and note all of the attributes of each class. And then it's based on these object interpretation keys that you create your logic rule set. And basically what that does is it lets you define a range of spectral and spatial attributes for each land cover class that you want to create. And then you run the rule set and you end up with all of those objects that you made earlier classified. So Once that classification is complete, the results can be exported as a shapefile to open up in something like ArcGIS Pro, and you get a result like what's shown here. And this is the classification based on high resolution Mount Hope imagery. So this is what object-based classification looks like from start to finish. The original high resolution imagery on the left, then segmented, and then classified. So here is where I ran into another roadblock, which is with my Douglas data sets. I wasn't able to identify specific attributes around where the grave locations were, that's those red markings, that differentiated them from other classes. So I couldn't move forward with this classification of a grave class. And then back to methodology, thematic map accuracy, which this slide shows an example, is usually used to determine how well object-based image analysis identifies known and clandestine graves for each image type. This method is commonly used to evaluate the accuracy of land cover class maps through the creation of a confusion matrix, which compares the ground truth points of each AOI to each classification result. So these are the results of this thematic map accuracy assessment for the Mount Hope data sets. Using buffered ground truth points, I ended up with NAPE grave classification results of about 86% for users and producers accuracy, and high resolution grave classification results of about 91%. So based on those results, the key takeaways of this capstone as they relate to my original goals are that using object-based methods are an effective way to identify known cemeteries, but ineffective in identifying clandestine graves within multispectral imagery, and also that high resolution imagery results in a slightly more accurate classification than NAPE imagery. So the last thing that I wanted to discuss is the possibility of future work. Had there been more time to spend on this project, I would have looked for a higher resolution source of satellite imagery to analyze, since I really believe that those extra bands could be beneficial in developing a useful interpretation key for the clandestine graves. I also would have taken the time to collect many more ground truth points in the field, not only of the graves class, but of other classes, so that my accuracy assessment would have more validity. And that is my presentation.
All right, thanks, Priscilla. Great job. Very practical kind of project. There's been a few MGI students in the past that have looked at kind of the same thing in sense of trying to identify graves in a cemetery that may not have, any kind of markers for. How, in terms of like the end user, how much more difficult would it be to use hyperspectral than multispectral imagery?
Well, I think because my original vision for this project was something that could be used by someone who doesn't have any GIS experience, that's why I leaned more towards this multispectral approach. I did not even attempt performing this workflow on hyperspectral imagery, so I can't say for certain how much more time intensive it would be, but that difference in that choice of wanting to use multispectral was more in the original spirit of the project, which was for these volunteers to be able to use something like this in an application.
Yeah. All right. Yeah, challenging project, certainly, and then implementation challenges too.
Maybe more of a comment than a question, but I can also foresee a very interesting similar object-based analysis where the object isn't necessarily one grave, but finding potential mass clandestine graves in areas around the world where you could probably potentially use a lower resolution data set because what you'd be looking for could potentially be far bigger, in some different areas of the world.
Yeah, that's a really good point. A lot of the previous studies that I looked at, uh, their applications were more towards these larger grave sites or mass burials. So, yeah, that kind of gives me some hope that maybe this coarser resolution satellite imagery could be used for that versus trying to sort of find a needle in the haystack with these, less than 1 meter sized individual graves.
My other quick question was with necro search, how often, I guess, in these scenarios are they maybe they know that a grave is potentially in an area, maybe the size of the Mount Hood graveyard. They don't know where it is in that area. Could they be flying like, a drone that's using hyperspectral so that they could be pulling the imagery that they need on a case by case basis where they're like, hey, we're fairly certain it's in this area. We can now use analysis to narrow it down rather than just, looking on humongous areas for just anything you might find.
Yeah, that's another really good point. And it helps kind of again have some insight into what my original vision was for the project, which was more for looking for graves of like an unknown location in these larger areas. But you're absolutely right that the application of using drones in an area where you have a better sense of where it could be located, yeah, it does make more sense to use a drone for that. But it's like I also wanted to just leverage this larger publicly available library of imagery,
Oh, totally.
keeping in mind that not everybody has the, resources to just go out and acquire using drones.
Mm-hmm. Sweet. Very cool.
All right. Thanks, Priscilla.
Thank
If
you.
you could put your contact info in the chat window, that'd be great. And then let's see, Chen Hao, I think you are up next.
Yeah.
If you
Everyone hear
wanna,
me?
yeah, we can hear you. Go ahead and try to share your screen.
All right. I am now trying to share my screen. Can everyone see my screen?
Yep, that's good. And we can
Yep,
hear
yep.
you, so you can go ahead and start.
All right. My name is Chen Haolu. My project's topic is the spatial analysis of relationship between educational attainment and 2024 presidential election results. First, my personal introduction. My current role is a program manager in Pacific Gas and Electric Company under Transmission Pipeline Integrity Management. It's a utility company. I think Priscilla, you're working in NV5. We use a lot of the NV5 products for our studies. For my responsibilities, I oversee and manage GIS programs and projects, ensuring transmission pipeline assets remain compliant with CPUC regulation and federal pipeline safety laws, and then drive some of these innovations and data integrity within the pipeline integrity programs. So for my overall motivation to start this project topic, I see a lot of the escalating political division since 2016. The overall division is very obvious and resounding. And recently, the political politician like Donald Trump gained popularity in this division. And not only in the United States, but I have seen this as a global phenomenon where right-leaning or right-wing politicians rising in Europe and United States. I'm really curious in whether how much educational attainment has played a role in these voting situations. And for example, we have seen political polarization in elections such as Brexit. And also, I have been looking into these kind of study ever since I started the program for my GIS certification. Throughout years, my target has become more obvious, and I decided to use this opportunity to do a deeper dive into this topic. So my hypothesis is that the educational attainment did affect 2024 presidential election results in the United States. I'm aiming to identify a positive correlation between educational attainment and votes for Democrats. So in this project, I have created maps and some of the spatial analysis to examine the trend. In this case, I'm hypothesizing that high-paying jobs requiring higher education are concentrated in major cities, and the spatial analysis will reveal these potential spatial relationship between educational attainment and voting results within these spatial analysis. From the previous literature, this has been studied from point to point. So one of the theory is education is a predictor for voting pattern. Higher education correlates with liberal voting tendencies, while ideology gap between college and non-college student has increased since 1969, but accelerated in recent years, especially in the past 10 years. And there are definitely two sides of the story. One would argue that liberal faculty member outnumbers conservative on campuses, and this heavily influences the ideology of college students. I would argue that some of the data that's generated in those studies are coming out from CSPS, which is right-leaning publication organization. So there might be some biases. Also, there are some other studies that stating the demographic characteristic like educational attainment offer limited predictability for presidential elections. One of the study followed students during 2000 all the way till 2004 across 38 institutions, and they did not find a significant shift of a partisanship of college students throughout 4 years. Although that study also was kind of tainted by the events of 9/11, where more nationalistic ideology was prevalent towards the end of the study. Some of the machine learning analysis has done this study and saying that educational attainment only represents a 63.5% accuracy in predicting voting behavior. In the conclusion, they said they believe this is not significant, although I will argue that in recent elections where we have within a margin of 3% differences, 63.5% is significant in terms of accuracy in predicting voting behavior. So for my data collection, I decided to collect total of 6 states in 3 different categories. Solid blue states that has been pretty solid for voting Democrat, such as California and Minnesota. Solid red states that has consistently voting for Republicans in the past 25 years. That's Texas, Kentucky. Also, I have included 2 swing states in the study. That's Michigan and Pennsylvania, that they have been switching to different sides in the last 25 years. So the data components, so I have the state boundary shapefile to get them into different spatial data correlating to the voting results and the educational attainment. These data are mainly coming from different census data from each state. The presidential election voting results by county is also coming from each of the states. 2024 educational attainment with bachelor degree or higher by county. This data is coming from the Federal Reserve Bank of St. Louis. So for the method, mainly it's gathering the data and clean them up and categorize the voting results into 3 different categories: the Democrat, Republican, and the others. We'll be ignoring the others since this is mainly focusing on the voting tendency towards a Democrat. And then joining the data and create these maps to create visual maps and looking for visual patterns first, and then finally using ArcGIS Pro to calculate spatial regression value and create scatter plot to see the regression relationship using the multi-scale geographically weighted regression model. So really quick visual identification. This is the voting results for Democratic candidates using 45 to 55% range as the middle class with 7 classes. The redder color, it is the less likely, the less votes for Democrat, meaning they voted for Republican more. The blue color means they voted more towards the Democrat. Not much of surprise to me with my hypothesis that mainly the Democratic votes are focused on major cities and along the coastal areas, while the rural areas are mainly dominated by Republican votes. This is the results for all 6 states for educational attainment with a bachelor degree or higher. I use the 33% to 37% range as the middle class with 7 classes because on national average, we have 35% of the population that is having a educational attainment with a bachelor degree or higher. Again, this is very similar to what we have in the voting behavior with few exceptions that later we'll find out that they are mainly concentrated in the cities and the rural areas are less educated if we compare these 2 photos. So due to the time constraint, I mainly focus to pull the map for California here. So by comparing these information here, I use the natural break that's setting the middle class as basically the mean range for California. And we can see that educational attainment has a strong correlation visually with the voting pattern here. Again, each state has shown very similar behavior, although there are we'll find out there are some exceptions once we get onto the regression model. Okay, so summary stats for the coefficient estimates generated by the MGWR model for California and the rest of the states, but I will mainly use California as an example here. MGWR model is the regression model that I ran through ArcGIS Pro. It's mainly for situations like we have a dependent variable and the independent variable that varies across space. Each state, even each county has their own curriculum on their education, and they have different fundings, different quality of staff. So education can vary across different spaces, and MGWR model can best represent that factor when we are performing this analysis. So in here, we have a mean coefficient of 0.8249, meaning implies that for every 1% increase in educational attainment, that will transfer to 0.8249% of Democrat votes across California counties. We also have an R-square value of 0.8636. That means 86% of the variation in voting outcome across all observations is explained by this model with a high model fit. 24 neighborhoods and 100% statistically significant coefficient means that this is a consistent influence of education on voting outcome across all regions within California. And if we look at the rest of the results here in Minnesota, Texas, Kentucky, Michigan, and Pennsylvania, they all shows very high coefficient mean except Texas. And then also they do have a high R squared value as well. If we look at the neighbor percent and the significant percent, that represents how educational attainment can be influential across our region. They have shown that the educational attainment, in fact, affects our region each state except Texas. So with the scatter plot, this also shows that they represent a positive correlation between educational attainment and voting results towards Democrat, except again Texas, that it has a R square value of 0.06, which is barely a positive correlation value. So in the conclusion here, we have determined that except Texas, all other 5 states has represented a positive relationship, a very strong positive relationship between educational attainment and voting results. And then spatial pattern and the MGWR results indicate this influence effect in most regions, if not all regions in each state. Educated people tends to concentrate in metropolitan areas, leading to higher Democrat votes in these areas, and educational attainment affects the voting outcome in 2024 U.S. general election. I think what this brings out is first, Texas is a very weird place compared to the rest of the study. I have results where it shows the more education it gets, the more favorite votes Republican gets, which is the opposite of what we have seen in other states. Some of the regions in Central Texas has shown this opposite behavior, which in this study was unaccounted for. And I'm very curious what has caused this situation. Only 35% of the voting results was represented by educational attainment, meaning some of the other factors that wasn't accounted for has affected the voting results in Texas, but not in other states. And also, I think this also brings the question for needs for further investigation into how higher education institutions might influence students' political ideology and encourage further study or research similar to this in other countries to see if this is true. And this is my presentation. Any questions?
All right, thanks a lot, Chen Hao.
Yeah.
Very interesting set of tools and conclusions. So if anyone has a question, that'd be great. In the meantime, I wanted to kind of ask you, I guess just a comment. Did you consider looking at the Akaki information criteria index over and above what your R square value was?
I'm sorry, can you repeat the question?
So you reported your R squared value as a measure of model performance. There's another metric called the Akaki information criteria, the AIC.
Oh, yes.
Did
So,
you?
AIC was not included in this study, but I did have the results for AIC. For RGS GW MGWR model, AIC is 393.
All right. So yeah, just each of your models would have a separate AIC value, and it's just another way of assessing the overall model performance.
Right, yes. So I did try to compare it to ArcGIS GWR model, which wasn't accounted for a local variation. It has a less accurate AIC value or higher AIC value, and the GeoDa spatial lag model has somewhere around 398, and the basic model has a value of 416. So out of the four model values, I got the best results for ArcGIS MGWR model, and that's how I come to the conclusion that I'll use this model for the study.
Okay, all right.
Yeah.
I was just checking on that. Does anyone have any questions?
I'll chime in here. Can you hear me?
Yeah.
Awesome. Hey, so this is Ryan. I just wanted to say I'm so sorry that I missed the most of your talk, Jinhao, and Priscilla, Zach, and Sarah. I missed your talks. This weather situation was bonkers. So I'm very sorry to have missed your talks, although I've seen earlier iterations of all of your work. It's really awesome what you've done. So anyway, so I'm on the call. I'm gonna let Fritz continue to drive because I keep getting messages that my connection is unstable even though I have power. So anyway, I just wanted to check in and just say hello to everybody, and that I look forward to the next couple of talks. Anyway, hopefully I'll stay online.
All right. Thank you.
All right, Chen Hao, if you could put your contact info in the chat window, that'd be great. And then I think Noah, you are up next. So if you want to share your screen, we can get rolling.
Already. How is everybody doing? Can you guys hear me all right?
I can hear you fine, and we're almost seeing your presentation yet.
Alrighty, it's loading in. So, almost near the end, everybody. My project is called Here Comes the Sun, If It Can Get a Permit, a GIS playbook for solar parcel prospecting. My job currently is working for a renewable energy group, and I help find and create the work and help design the workflow for finding where in the world can we build solar. So the project is using a GIS-based, obviously, methodology for trying to find viable sites for solar development. We're looking at integrating technical and environmental and regulatory data, and we're looking at things on a parcel level, which might not seem intuitive at first, but dealing with one landowner is easier than dealing with a lot of landowners. We're looking at things on a 25 plus acre level and looking for about 3 to 5 megawatts. So we'll go through this. I'll try and be quick, and we'll talk about the background, the data, the methodology, and I'll talk about some of the results of some of our recent searches. In the literature review, there's actually a lot of gaps. There's a lot of chat about the technical feasibility of such a process in mapping solar potential by looking at solar irradiance and albedo, and there's a lot of very cool tools for figuring out how much solar a actual area of land can produce, given its slope and radiance and time of year and amount of sun, so on and so forth. There's papers about refining site selection with LiDAR and using locally flown drone footage to try and optimize where we can actually place panels and whether tracking versus stable racking would be better. And there's papers written about solar planning in terms of local governments. There's papers about the ecological impact, about integrating environmental risk factors. There's a lot of work here, but a lot of what the actual the gap is looking at this on a parcel level and also addressing sort of some of the issues as to why solar is not being built that fast. And a lot of the research points to, or some of the research points to, a lack of federal regulation and certain laws, but I argue that it's due to data acquisition issues. And so we'll talk about that here. So in terms of data, we're going to utilize 8 data sets to kind of start to build these maps. We'll use Elevation models, which is obvious. The interconnection, which is our big issue here, is that most utility companies do not like to post very detailed interconnection maps for a variety of reasons, whether it be critical infrastructure and it could be a danger. Maybe they just don't have the internal pipeline for actually publishing their data in such a way. And so a lot of the maps that you get are actually incomplete. They're cobbled together. They're not updated frequently. And so this does present a lot of challenges because one of the quiet aspects of finding places for solar is there enough room on the grid to put a project there? The land could be perfect, but if the grid is full, you have to pay for upgrades, and we'll get into that. So this project takes place in New York because New York has some of the best utilities for this, being NYSEG and NGrid. We're going to look at wetlands and floodplains. And all of these, especially wetlands and floodplains, we like to look at the most local level possible because local jurisdictions often have better data. And the further out you go, say New York State, the data gets a little bit less granular. And then when you go to a national floodplains inventory, it becomes less granular again. We're also taking into account all the local ordinances for all the different municipalities, localities, and counties. Ordinances are really important given setbacks, where you can build, where you can't build. So ordinances and zoning kind of go hand in hand. We need parcel data sets, which normally we can pull from local municipalities, but a lot of the times you have to find them from the state or even larger. You've got to pull together multiple data sets. You've got to join addresses to shapes and buildings to parcels and so on and so forth. And then we also have a buildings shapefile that we're working with specifically for New York because New York is great enough to provide a singular file that provides every single building in the state of New York as of like 2022, which is really, really, really useful. In terms of a methodology, and sorry if I'm talking a little quick, there's kind of a lot to go through. In terms of hardware, we're using ArcGIS Pro. We're going to do a little bit of coding with Python and ArcPy. We did some backup research with QGIS just to see if this could be done by other groups for free or to try and see if we really needed to use Arc to do it. Realistically, we don't really need to use Arc to do it, but given that I'm the most familiar on Arc and that's what we use at my company, this is all done in Arc. All of this data is acquired as local as possible, like I said. There was a lot of, one of the big breakthroughs in it was starting to use GIS REST servers to pull data down, and a lot of these REST servers are necessarily Googleable, and they're not accessible through the portals for interconnection or zoning, but you can do things like look up Yates County, New York.gis.rest server, and they all follow the same syntax. So you can actually oftentimes brute force your way to find a REST server that exists and it's open, and then you can instantly pull all of this data into your map, which is incredibly useful, as opposed to having to do some other sort of cobbling together. And this really increases the speed at which we can go through counties. Really, we do an initial parcel screening and filtering to try and get rid of any garbage that we just don't want, whether it be too small, too far from interconnection, bad zones, and we'll talk about this in detail with the results in a moment. And the real goal is to try and get to a list that has parcels that meet all of our general criteria, other than interconnection values, which we'll get to. Zoning compliance and review is one of the last steps that we do because zoning compliance can change at the drop of a hat. And one day a county can love solar and the next day they can place a moratorium for 2 years. But the reason why we actually do zoning compliance last, I'm arguing here, is that since it changes, if you've done all the work to figure out if parcels are good, if zoning changes, or the rules change, you instantly already have a shapefile with all of the potential parcels in a municipality. And so if as soon as the municipality is lifted, you can have such a program that takes the date, it emails you, hey, this moratorium is lifted. Here's the location of that shapefile that you made. All these parcels are good to go. And then you can hit the ground running on those parcels. And we can really try and keep the ball moving because we're really trying to build renewables kind of as quickly as we can. And then we also do, near the end, we do an infrastructure proximity analysis. This is mainly to three-phase lines and substations. This is the very complicated part. which is mostly left to kind of out of scope to our electrical team, because on these lines you will get something called distribution capacity and thermal capacity, and these are values for how much energy can be put onto a line or into a substation. And not only are these data points not frequently updated in all areas, sometimes they're just wrong. And there is not a way to automate whether or not a project could fit on the grid. One example is, let's say that you have a line that does not have enough capacity, and you've got a substation that doesn't have enough capacity, but you're building it right next to a factory, like a big solar farm next to a factory. Theoretically, all the electrons leaving that factory are going to go in, or leaving the solar farm, are going to get onto the power line, and then they're going to go straight to the factory because that's where it's going to be used next. And it might only actually be placing a load on 2 or 3 nodes of the grid, and it doesn't actually ever go to the substation. And that's kind of what an interconnection study will look at, which is beyond the scope of this. That's a $10,000 thing that you have to pay the utility company to do, and then they tell you whether or not your project will work, or they tell you if you have to pay a lot of money to upgrade things. In the world of developing solar, we normally do about 3 miles to a substation because it's about $1 million per mile to upgrade a line, and things under 3 miles normally pencil in areas where there are incentives to build solar. And so then the final steps is really, after all the filtering is complete, I make maps that are the final data set that combine the parcels, any wetlands that we find, acreage, phone numbers, landowner names, and we have, we refer to him as Mr. Rogers, who is the nicest man I've ever met, and he actually lives in these areas, and he goes out to these people and he sits down with them across the table and he asks them what their plans are for the future. And if they see solar on their farms as a potential option. A lot of people really don't want to do that, and that's completely okay. A lot of people are, 7th generation farmers whose kids don't want to farm the land, but they don't want to sell it, and they see solar as a really good option. There is an entire other side of the political landscape and the local stakeholder navigation and local governments that is incredibly complicated and not GIS focused, that I'm kind of going to leave out of scope as well. That's the other half of my job is local outreach and like answering questions for people, and holding public meetings to try and educate people on like what's going on and seeing where they're at. But that's all after we at least get all the parcels. So results. This is just for Yates County, New York. Since I started doing this project, I've done this for 12 counties and like 60 municipalities in New York. And I'll let you know where we're at with that at the end. So specifically with Yates County has almost 16,000 parcels. Of those parcels, 1,600 are over 30 acres, and only 422 of those are within a reasonable distance of three-phase interconnection. All of these green parcels pass the first basic litmus test. So we're already down 15,400 parcels. Super fast code chat because we're going to talk about slope and wetlands. I did have to build a tool that will create an overlay. So you can take a slope map, or you can take, you can create a mask that says this is too sloped, or hey, this is a wetland. And I wanted to figure out, like on a parcel level, how much of this parcel is wetland. And there wasn't really a tool for that. So I built a tool that can take another shape and overlay it, and then calculate the overlap, and then add that back to the original file, like as a field. And this just does that. So you could do this for anything. You could, if you wanted to know how many acres of a forest changed, you could create a mask of something that was the change, and then you overlay it on your original, and you could say on a parcel level how many acres of each parcel changed. There's a lot of cool application for this. This was not supposed to be the main project, but this was actually really, really fun to code. If anyone has any questions about this, my email will be in the chat. I will totally answer your questions and talk about this, and I can share the code with whoever. So by doing this, we were able to get rid of 52 sites because they had too many wetlands, and 30 sites because of slope. You actually have to combine the wetlands and the slope together to dissolve them as one, because if a site is 35 acres and it's got if some areas can be too sloped and wetlands, and so maybe you've got they overlap, and you actually do have more than 30 acres left. But if you considered them separately, you would have less, if that makes sense. So it looks like actually 82 parcels would get disqualified, but it's actually only 73 because 9 of those are due to overlapping areas. So 350-ish parcels left. Once we take a look at distance to interconnection, cost to upgrade, so on and so forth with substations, we cut about another half of these parcels down. And then beyond that, we finally do zoning. And only 2 of these municipalities in this county have any type of compatible zoning, and they want it to be on agricultural 1 land. Some places like residential, some places allow you to do it on industry. Some people like it wherever, some like it nowhere. For these 2, Torrey and Potter, they wanted it on ag. And so of our original almost 16,000 parcels, 28 parcels meet all of the criteria to potentially have a 3 to 5 megawatt solar array built on them. And then we build these fun little maps. You'll notice if you count carefully, this is more than the number I just said. For example, these bottom left 2 parcels were tossed out, but they're actually, once you build these maps, you can see these are all owned by the same guy. And so I like to keep those together because then you know that this entire area could be done as one project because it's a singular landowner and your setbacks only count when the landowner is going to change. So you actually would need a setback along this parcel line. Since starting this project back in January, Yates was kind of quicker to do because it was a little bit smaller and I've done a lot of them. And we're looking at by June, hopefully having close to 70 megawatts under contract. Doesn't mean they'll get built. They still have to all pass interconnection studies. So that's up to the study. But that's enough energy to power 50,000 homes. And so this is also in a very saturated solar market, and most places are using pre-made programs like Anderson optimization and other types of programs that amalgamate large swaths of publicly available data. And so it was really cool to try and figure out how to do this separately, differently from them, to try and find parcels that have been missed by other developers. And it's been going really, really well. And so I'm really excited about this actually. And that's the project. Sorry if I talked really fast. There's a lot of information. Any questions?
All right, Noah, great job. Very interesting application. Anyone have a question for Noah?
I've got one question. So in Pennsylvania, parcel data can be really hard to get because each individual county produces and then distributes, or they get to decide whether or not to share their parcels. So there might be some places in a place like Pennsylvania where you wouldn't have parcel data. So I guess my question is, with this methodology you've developed, could you do it if you didn't have parcel data, or what would it look like if you didn't have parcel data?
So right now I'm working on pivoting this workflow to Virginia because I live in the Shenandoah Valley. I do a lot of, we've built stuff here. I do a lot of outreach. We live in a very rural part of the Shenandoah Valley, and people are very on the fence about solar. And Virginia's data is awful, like god awful. Dominion keeps it a secret. The parcel data is all secret. And so this workflow really works for New York. It would 100% have to change. We're doing this on a this is a county and municipality and parcel level, but realistically it has to be as granular as the entity making the rules and sharing the data. And so it would change for different areas. So I've pivoted this to work for battery storage in Massachusetts recently. Massachusetts has all of their data statewide, so it's very, very simple. But like you said, with Pennsylvania, I would actually identify first. I would go pull together all of the ordinance data, and then I would target like a Venn diagram of places where the ordinances are good enough, and also there's incentives and they provide data. Because I mean, if they don't provide the parcels, you can't do it. So you would actually just have to look elsewhere until such a time that you could figure it out, because there's really no way to do it. Like a lot of the prior research looks at like large swaths of area around cities in Europe, like it's all Europe. And so there's different rules and it's much simpler when the government's trying to do it. Well, quote unquote simpler. It's more like eminent domain, but to try and get a bunch of landowners to work together to have a big project. But in the US, you kind of have to do it on a parcel level. So
Okay.
yeah, to answer your question, you'd have to avoid places where you don't have that data, unfortunately, I think.
Got it.
There is the possibility of, depending on who you have on foot, of identifying areas and then making phone calls to different chapters and regions and, Kiwanis clubs and things like that. Like we've done that too. Like it's a lot of it's a lot more local outreach and conversations than you'd think, which is why like almost like 90% of this project process is not automatable. It's like each of the steps themselves have certain aspects of it, like the colors and the reprojections and so on and so forth, but actually the decision making part of it is a very human aspect.
All right, now thanks again for a great presentation.
Thank you.
If you could put your contact info in the chat, that would be greatly appreciated. And then I think Boris, you are next in line.
Yep. Let me try to put my stopwatch here and share. I think somebody else is sharing, so I'm going to request.
Yeah, no, if you could unshare. Thanks.
Cool, you should be good to go now.
Yep. What do you guys see right now? Is it a PowerPoint?
Yep, we can
Cool.
see it. So whenever you're ready to go ahead.
Okay, so my name is Boris Ladievich. This is mapping public parks using custom OpenStreetMap data. I just kind of want to preface with this that this isn't really a traditional analysis. This is more of a proof of concept of building a GIS with open source technologies, sort of from the ground up, with results. So a little bit about me. I am a senior GIS analyst at a water engineering firm, Hazen and Sawyer. We deal with all things water, so stormwater, wastewater, drinking water, potable reuse. We do a lot of pilot research. We design at the inside the fence, we call it, at the treatment plant or the conveyance systems. A lot of stormwater modeling with image classification. There's a small GIS discipline within Hazen, and I'm part of that group. Parts of my responsibilities are to develop sort of online map applications for internal, external users. All of our clients are public utilities, essentially. I do a lot of analysis and modeling and other various, in-house tool developments or for delivery for clients. Some of my bigger projects, at least in the last 2 years, was developing these public-facing web experiences for the lead and copper rule revision, which is a federal mandate that every public utility needs. They need to provide a service line inventory of everybody's service line and continuously update and maintain that to ultimately have the goal of 100% lead-free verifiable service lines. Among other things, I try to mix into a lot of different water-related projects. So why did I choose project or parks? The kind of generic reasons, I myself, I love parks. I visit many different parks for different reasons. I do biking, I play a lot of tennis, sometimes I do pick up basketball games. The general reasons, really, I mean, there's, physical and mental health benefits. The big emphasis here is free recreational activities available. They promote social interaction, and a quality park is kind of a cornerstone of a solid community. But really, this is a sort of a hobby project for me. I'm trying to get accustomed with using open source technologies in GIS. At Hazen, we use exclusively ArcGIS, which nothing against ArcGIS. I started my career that way. I have an Esri shirt on right now, but I wanted to wet my feet with open source GIS and realizing now it is a vast landscape and honestly overwhelming landscape. So this is just an experience builder app that I built that kind of captures the essence of what I'm trying to do. This is mapping just a bunch of parks, just all the parks available in Pinellas County, which is sort of the county that I'm from. And this is from the Pinellas County official government OpenGIS hub. This is their official data. And then you can see here, I'm sort of filtering the tennis courts, and all of this stuff has different attributes. The problem with this is the next county over doesn't have the same schema as Pinellas County. And then that county over might not have the same schema as that county. Some counties might not even have public park data. So there is no universal standard or schema available for just public recreational parks available that people can identify, filter, and look for different features in them. Oftentimes incomplete, inconsistent, like I said, unavailable. So the goals of this project and the objectives is to develop a large-scale general purpose park data set that has information on what recreational activities are available: basketball courts, tennis courts, baseball, volleyball, what other amenities are available. Is there a dog park? Are there benches? Are there bathrooms, water fountains? Using OpenStreetMap data. And then also to create an interactive map for finding these parks, along with all the other pieces that the backbone of this system. This is to be Florida-based to start as a proof of concept, but the idea is that OpenStreetMap can be used to do this at a much larger scale. This is for the state, but I ultimately want to do this for the entire country, really. All using free and open source technology so that this stuff is accessible. So OpenStreetMap, if you guys aren't, some of you might be familiar with OpenStreetMap as a base map, but at its core, OpenStreetMap is really a database. It's a highly structured database with nodes, ways, and relations, which you can kind of think of as points, lines, and I guess polygons. And then also tags, which is kind of like your attribute data. There's been a successful and steady increase of use of OpenStreetMap since it came about in the early 2000s. It is in fact the largest GIS crowdsourced data set available. It is a gold mine of GIS data. It's also proven to be accurate. Oftentimes even as accurate as official government data. So open source GIS, again, I wanted to kind of dabble into this field, but also because of the fact that it's highly accessible for people, no really paywalls. A lot of the source code is open and you can customize it, so there's a lot of flexibility there. Open source GIS uses a bunch of standards as far as file formats go and things like that, and other specifications which have long-term viability. There's, again, strong community support using open source GIS data and a large pool of developers that are always there to help you and respond to problems or other technical issues. So again, the data for this project is to strictly use OpenStreetMap, but it's going to be a custom derivative of it to get my schema in the format that I want, so I can map all these parks out for the entire state and ultimately the entire region. So these parks will be obtained through OpenStreetMap through their leisure tag. That's how you identify a park. And then the recreational activities that are available in them through a variety of tags or combination of tags. And this is, again, all for Florida. So a basic overview of how this happens is the raw OSM data needs to be extracted, transformed, and loaded into my own custom database with a custom schema that I developed, that I designed, and then have a mechanism to be able to publish the data that I produce in a format that some interactive mapping application can consume. And then I'll of course develop that mapping application to kind of bundle everything together and show you that it's the overall proof of concept and that it works. So these are the main tools that I used for this project. OpenStreetMap as data and a tool as well. Initially, I wanted to use Overpass, my own instance of this API called Overpass that is from OpenStreetMap. I could not get this to work. I was spinning my wheels too much. I'm new to Linux, and I did all this on a Linux on a new computer. So I found I had to back down and find an alternative solution. I found a website called GeoFabric that essentially serves out raw OpenStreetMap data in bulk. And so I was able to download the latest, all of the features available, every single feature from OpenStreetMap in Florida. And I used a command line tool called OSM to PGSQL, which takes my raw data and then imports it into the database management system that I use, PostgreSQL, with an extension called PostGIS, which allows you to do some geoprocessing at the database level with SQL. GeoServer is sort of the server that's going to transform our data from Postgres into this servable format so that my map can consume. And then MapLibre is it's an open source mapping SDK that I'm using for this. If you know or have heard of Mapbox, this is the open source version of Mapbox before they went private. So the methods, a little bit more detail here. Again, I downloaded raw OSM data that typically can't be processed by itself. You can download this stuff as shapefiles, but it would be a gigantic shapefile. So I downloaded this in the native OpenStreetMap .osm file format, .pbf for the zip, I guess, from this website for all of Florida. I used my command line tool to convert all of that, import it into my database. So now I have every feature available in a table for all my lines, all my points, all my polygons, for every single feature in Florida. And then I built through SQL. This is me just building an empty table, an empty shell that's going to be my schema, including all the columns that I think are necessary to be able to produce sort of the interactive map that I want. And then this is kind of showing me loading some data that I'm not going to do any processing, but I can just load directly into my custom table from the raw tables that I imported. And then I use PostGIS for geoprocessing. This is probably the most important and most crucial step. There's a lot of blocks of statements here, but they're doing all the same thing. They're basically taking my table that I now have all parks for, and intersecting them with the raw data, and I query the raw data if there's a tag for example, tennis. So I query that, and then I intersect those and see for this specific park, is there a tennis court in here? If so, assign a value of 1 in that column, meaning yes. Null for it doesn't have a tennis court. So I did that for a variety of different features, a variety of different sports and amenities and things like that. And so here's just a resulting table. I think overall there's like 8,700 total publicly accessible parks in Florida. This is just a snippet showing that there are at least 883 public parks that have at least one tennis court. For basketball courts, it was like 1,200. And then, I can't even imagine for the rest of those sports and amenities. So this data was then loaded, and the data was configured from PostGIS into GeoServer. And I also, there's a lot of that kind of goes on here, but one of the things I had to decide is what file or what format, what geospatial format do I want to serve? What geospatial format do I want this to be consumable in? I ultimately chose something called Mapbox vector tiles. A lot of reasons for that, a lot of pros, fewer cons in my opinion. Too much to get into why, but this is ultimately what I chose. But I can also provide my data as any kind of service, really, as a web feature service, web mapping service, different roster types, whatever I want. But I chose Mapbox vector tiles. And this is a preview that GeoServer has that kind of shows what those parks look like. I wanted to make sure my projection's okay. Everything kind of loaded in fine from my PostGIS database, and it looks like it did. So, and then from there, I developed a the web map application for this. Like I said, I used MapLibre, and with a few additional plugins, I used a CSS framework called Bootstrap to kind of stylize my website, I guess. And this is just a snippet of some of the code. On the left is the JavaScript, and then the HTML and the CSS on the right. The main thing to look at here is line 88 shows the file format, which is basically me requesting the service of my Mapbox vector tiles that I just created in GeoServer that are from PostGIS that are ultimately derived from raw OpenStreetMap data. So this is sort of the format of that, and it allows the user to be able to open up a map and actually see the parks and things like that. Some of the features of the app, there's geolocation, so you can type in an address and find a park. The big thing again, what I showed you before was that experience builder app that filters out sports, but that was just confined in Pinellas County, in one single county. This is now for the entire state of Florida. So this is me kind of just filtering the points, and then when you click on a point, there's some park information. There's a base map switcher. I forgot I had the demo. But so here I'm just showing myself sort of painting across Florida, just a section of Florida showing all of the different parks. And again, what I showed before was just Pinellas County. That was all that was available. This is all in the same structure, same format. And I'm able to map this out and serve it out for my own database, for my own server, my own GeoServer, and all that stuff. And here I filtered out every park that has a baseball field, for example. I'm seeing all the other features that are available in there. And then I kind of wanted to double check some of this stuff. So I added a satellite image, and you can see, in fact, this does have a baseball field. So some of the conclusions here, again, my goal and my intent here was to show a full methodology, a full proof of concept of how you can build something like this. It is really meant to be a general purpose mapping tool for mapping these parks and being able to use the data at some point eventually, so that you can identify trends in locations in parks depending on the features they have. Again, this is it's universal, it's a standard schema, so it makes it scalable. This is just Florida, but there's really nothing technically stopping me from building this for all of the United States and eventually moving it to different countries, different continents. The data is reliable, it can be reliable. The data is accessible, it can be accessible. Anyway, so that is my project, I believe, and the rest are nothing.
All right, thanks, Boris, for your presentation. Kind of maybe a more comment than a question. So, assuming that you keep working on this, what kinds of user testing would you envision to make this sort of consumable at the end user level?
User testing as in testing the app that it works itself, or the data being reliable?
Well, I mean, both of those would be important factors, right?
Mm-hmm. Yeah.
Yeah.
So the big thing is, how reliable can the data be? It depends on your region. Obviously, a lot highly urbanized regions with a lot of technology and a lot of smartphones and things like that will likely have more data in the OpenStreetMap database that I'm able to kind of extract and map and things like that. One of the features that I envision doing for this project, which I know there's another map that has done. It's called Open Beer Map. If you Google it real quick, the person who built that has a feature that you can click on, for example, a pub in like London or something, and you can in fact update the attributes from the app itself, just the attributes, and it'll upload those to the OpenStreetMap database, the one that the entire world can see. So maybe a feature like that allows people to go to a park and realize, oh, this tennis court actually doesn't exist, remove it, or this tennis court is not lit up, remove that tag from this, and things like that. As far as other kind of QC checks, as far as the data goes, there are internal topology checks that OpenStreetMap themselves kind of implement. So a user can't just put a skyscraper on top of a skyscraper. So that's what I meant by the data is highly structured and formatted and organized. But again, also like user interface and things like that are going to be important. So maybe show this to friends and family and see what they think. Does it work right? Does it look fine on mobile? How does it interact? Is it slow? Is it fast? So just general feedback.
Yeah, I mean, all that's very logical. one of the things I was thinking of when you talked about, like attribute accuracy or even positional accuracy is, in cartography, there's ways that you symbolize uncertainty and how that could be brought into your symbolization palette.
What do you mean by symbolized by uncertainty?
Well, as you said, is there really tennis court here? Is there really
Right.
lights here? Is it really a, I don't know, an asphalt surface? I don't know tennis all that well, but there'd be different ways you could assess the reliability of the data in
Yeah,
regards to how you yourself are defining what's a tennis court or a baseball field or
correct.
um,
Yeah. So, another thing that I've thought of as part of implementation for a project like this, like I said, it's a hobby project that I want to continue. This data it's a structured database. What I envision also doing is being able to provide or have a sort of multi-model database that also includes unstructured data. So, for example, if a user goes to a tennis court or whatever, let's just do a tennis court, and they see, oh, this is not lit up, they can, for example, they can take a picture of it, of the area, and then you can see with that, when you zoom in, you click a point, you can actually see that there in fact are not lights there. Or if people want to see for a basketball court, is it double rim or is it single rim? Take a picture of the rims themselves, and then sort of have a multi-model database that can handle that type of those types of attributes as well.
Sure. Yeah. I mean, yeah, that all makes sense. Good. All right. Yeah, Boris, why don't you add your contact info to the chat window while I'm making some final comments here, and then we'll be able to wrap things up. I'd like to thank everyone for showing up and giving a great presentation. I appreciate your patience at the beginning while we sort of got things sorted out. Little weather issue here in central Pennsylvania. But yeah, thanks everyone for your patience, your cooperation. Congratulations on getting through the presentation component of your capstone. That's a big achievement, definitely. So I wish everyone a pleasant rest of their day, evening, wherever you happen to be. And there's another presentation, I believe, tomorrow, Wednesday. Please make sure to stop on it and see your other colleagues and listen to their presentations. All right.
Thanks, everyone.
Have a good night, guys.
Thank you.
Thanks.